Water heater control system simulation in Simulink. There is a water heater that should keep the water at the temperature of 70 degrees Celsius. The water heater consists of insulated tank, the water, and the heating element. Initial water temperature is 20 degrees Celsius, and our task is to simulate water heater behavior in time. First, let's build the simulation model in QuickField. I start QuickField and create the new problem. The problem name is the tank heater, and the folder is this one. The problem type is transient heat transfer. The model class is axisymmetric. This model class is suitable to model cylindrical bodies. Length units are centimeters. Click Next. For transient problems, we should specify the integration time and the time step. Well, let the integration time be 2 hours and the time step 1 minute. Yes, and the initial temperature is 20 degrees Celsius. Okay. Here you can see the geometry model editor window. The axis of rotation symmetry is a horizontal one. So in the model, we should draw only the upper half of the cross section. I will use the Insert Shape tool and I will insert the rectangle. The width of the rectangle is 0.6 and the height is 0.3 meters. Oh, we have the units of centimeters, so 60 and 30 here. The insulation thickness is 4 centimeters. So the next rectangle will be located here, 4 centimeters, shifted to the right. Height is 26 centimeters, and the width is 52 centimeters. Okay. Now I will draw the heating element. Switch to the Insert mode and click and draw the lines. Next, we should assign labels to the objects. Through these labels, we will later assign physical properties. I switch to Select mode, click the object to select it, and open the Properties window. Here I should type in the label name. This is the heater. Okay. This is the water. Okay. And this is the insulation. Okay. And we have the boundary. You should hold the Control button pressed to select multiple objects. So these edges I will label as boundary. Now let's assign physical properties. Double-click the label to open the dialog. For the heater, I specify thermal conductivity of 100, heat capacity of 100, and the density of 6000. It is just some piece of metal. For the insulation, double click. I specify thermal conductivity of 0.1, heat capacity of 1000, and the density is 800. For the water, thermal conductivity is 0.6, heat capacity is 4200, and the density is 1000. Okay. On the external surface, the tank is in contact with the air, so I can specify the convection boundary condition. The air temperature is plus 20 degrees Celsius and the convection coefficient 3. Now let's run the analysis. Well, we have to build the finite element mesh, save all simulation files, and then we can start the simulation. The simulation process is finished and we get the temperature of 20 degrees Celsius. That's because we have not specified power source in the heater. Okay, I will open the label properties. The power of the heater is 2 kilowatts, but I should specify power density. Power divided by the volume. So I will switch back to the results, use the contour tool, select the heater element, open the integrals, and here is the volume. Oh, I should switch to meters. View length units meters. Now I can copy this value again, open the heater block properties and type in power divided by the volume. That's it. Okay, now let's run the analysis again. And we have the results. The water temperature is above 100 degrees. And we know that the water will evaporate and the tank will explode. QuickField doesn't know about it, but we know that the water temperature should not exceed 100 degrees. Well, let's check the water temperature variation in time. I right-click here and choose the time plot. So, to preserve the tank, we should keep the water temperature below 100 degrees Celsius, and we should limit the heating process by 5,800 seconds. Okay, I go to the problem properties, switch to the timing tab and type in 5,800 seconds. Okay. Yes, we will do the analysis again. Run the analysis. And here we got the result. The temperature is 100 degrees Celsius. Now at this moment of time we should switch off the heating element. To simulate this process, I will create the new problem. Tank heater 1. Again, it will be transient heat transfer problem. Length units are centimeters and the model class is axisymmetric. Next. Okay, let's again set the simulation time to be 2 hours and time step to be 60 seconds, 1 minute. And the initial temperature is, well, in first problem the temperature was distributed uniformly and we can specify the initial temperature for the model, for entire model, to be 20 degrees Celsius. Now the temperature is not distributed uniformly, so we can specify just a single value. We need to build the link from first problem to the second one and export the temperature distribution. To be able to create the link, both problems should share the same geometry model file. So I go back and here I will browse and find the geometry model file that is used by the first problem. Okay. Now I have two problems. The problem where the heater is switched on, or I should, you see, these problems share the same geometry model file, but the data files are different, so I should assign physical properties again for these labels. I will simply move labels from one problem to another. So this problem simulates the heating process. The heater is switched on. And in this problem, the heater will be switched off. I will specify 0 power source value. Now I should create the link. I would like to import temperature distribution from the first problem. So in this problem, I will open the properties, switch to the links tab, specify the link type, temperature field distribution, and specify the problem. I would like to take the temperature distribution from this problem. And I add the link. Well, for the transient problem, we should specify the moment of time. This is the moment of time, 5,800 seconds. Update. Okay. Now we have the link. We get the temperature field from the tank heater problem. Now let's run the analysis. Okay, we have switched off the heating element and simulated 2 hours long thermal process. You see the temperature drops below desired 70 degrees Celsius. Again, I can take a look at the temperature variation in time. So our goal is 70 degrees Celsius. And after about 20 minutes, we should again switch on the power source. So I open the problem properties and correct the timing. Now it's 1200 seconds or 20 minutes. Let's run the analysis again. And let's take a look at the temperature distribution that was at the beginning of the process. So it was 100 degrees. And minute after minute, the temperature was diminishing. So after 20 minutes, the temperature was only 70 degrees Celsius. Now we should switch on the power source again. I should create next problem based on the same geometry model. And in this new problem, I will take this temperature distribution as an initial. The heater will be switched on. And again, I should run the analysis. When the temperature rises to 100 degrees Celsius, I should switch off the power source again and simulate the next problem. So far, we ourselves acted as a control system, manually switching on and off the heater. Now let's build the automatic control system. Before building the control system, let's adjust the problem setup. To limit number of problems in chain, we will build the closed loop of just 2 problems. To make a loop, we should put the reference from the first problem to the second one. Okay, I will open the problem properties, go to the links, temperature field, and put the link to the second problem. Final time 100. Okay. Now we have the closed loop. Second problem links to the first problem, and the first problem links to the second problem. To make our control system agile, we will shorten the simulation time. So in the timing, I will set the calculation time to be only 1 minute with the intermediate time step of 10 seconds. I can run the analysis. Okay, now only 1 minute is simulated. And for this problem, the same. Open the problem properties, go to the timing. Only 60 seconds will be simulated. Okay. Inside the loop, the state of the power source doesn't change. So we can use the single data file for both problems. So I open the problem properties. And I will use the same data file as in the first problem. So if I change the power source to be 0, run the cycle again. I will simulate the cooling process. And if we run the cycle again, we will model next 2 minutes of the heating process. Now we can build the control system. The control system will run and count simulation cycles, measure the temperature, and switch on and off the power source. We have 2 QuickField problems connected in a loop. Now the power source is switched off. So if we run the loop, the temperature remains 20 degrees Celsius. The geometry model file is shared between these 2 problems, and we have the common data file. Each problem simulates a short interval of 60 seconds. So if we run the full cycle and simulate both problems, then we will model 2 minutes of real-life process. Now let's start Simulink. Here is a simple control system in Simulink. We have a goal temperature, which is 70 degrees Celsius. This block subtracts temperatures, and we get the difference between the goal temperature and the measured temperature. Then we have the relay block, and if temperature difference is positive, or in other words, if the measured temperature is below the goal temperature, we switch the power on. If the temperature difference is negative, then we switch the power off. To prevent rapid switching off and on, we allow 5 degrees Celsius bandwidth. That is, if we hit the goal temperature, we switch off the power immediately, but then we will not switch the power again until the temperature drops 5 degrees Celsius below the goal temperature. Now let's take a look inside the water heater block. The input of this block is power, and the output is time. And also we have the clock to synchronize QuickField simulation with Simulink time. Now let's open this custom function. Simulink may invoke this function repeatedly, searching for a way to optimize or linearize it. And to prevent misfire of QuickField analysis, we compare the actual time with previously stored time. And if the difference is 120 seconds or more, it is time to run simulation in QuickField. And the computation procedure includes 3 functions. First, we set the power on or off. Then we simulate a cycle. Then we store the current time in the file and measure the temperature in some specific point. Now this is the function that sets the power. First it gets the link to QuickField object, then it opens all problems, take the first problem from the collection, open the data file, get a collection of blocks. You see QuickField has collection of vertices, edges, and blocks. Vertices collection index is 1, edges collection index is 2, and blocks collection index is 3. So we get collection of blocks labels and get the item with the label heater. For the heater block, we set the loading, which is 0 for the switched off state, or power density, power divided by the volume. Then we save the data file. Remember that both problems share the same data file, so there is no need to change the power in the second problem. Once the power is set, we run the simulation. That is simple. We take a collection of all open problems and invoke the solve problem for the first problem and then for the second problem. And the last function is measuring the temperature. Again, we get the link to QuickField object, get the collection of all open problems. We need to know the temperature in the end of the cycle, so we open the second problem. The problem is already simulated, so we can analyze the results and get the result object. From this object we get local values in specific point. Field values include temperature, heat flux density, thermal conductivity, and other parameters. We need only a specific field parameter, namely the temperature. And we have some functions that read from the file and write to the file current simulation time. Now that is all. Oh, before we start the analysis, we should adjust the simulation parameters. Remember, one cycle models 2 minutes of the real-life process, so in solar parameters we specify the time step of 120 seconds, and the final time will be 1 day. Okay. And we have some functions that read from the file and write to the file current simulation time. Now that is all. Let's run the simulation. You see, the initial temperature was 20 degrees Celsius, so the relay immediately switched the power source on, and the water temperature starts to rise. And we run cycle by cycle and control the temperature. The temperature rises till it reaches 70 degrees Celsius, and the relay will switch off the power source. Then the temperature begins to drop, and when it hits 65 degrees, the relay switch the power source on again, and the cycle repeats. Simulation is over. This way you can build control system in Simulink that will interact with QuickField. In fact, that was very simple control system. You can do much more with QuickField open programming interface, you can create new problems, you can modify material data and boundary conditions, you can build contours, make plots, export field pictures, integral values, tables, and much more. In fact, you can use not only the MATLAB but any other software that can interact with QuickField application programming interface.